I want to talk to you about uncertainties, and I want to talk about them in the context of a specific example where we can imagine that we're trying to find how fast a little toy car travels. And the way we're going to do that is we're going to time how long it takes to travel a distance, a measured out distance that we measure out with a meter stick of that distance, and we're going to time how long it takes to travel this distance, and we repeat the experiment 5 times. So we time the car 5 times and we get the following data. Now I want to talk about uncertainties in general. The important thing to realize is that every measurement that you make has an uncertainty associated with it. So there are 2 measurements you measure. You measure the distance and you measure the time, and each of these measurements has an inherent uncertainty in it. And why do we care about that? Because your job as a scientist is to communicate the uncertainty in each of your measurements to other people. So if I say that the average time is t plus or minus delta t, what I am communicating to other people is that I am confident that if you repeat my experiment, okay, and we put the measured times on a number line, I am confident that you will measure the true value of the time for this trip somewhere between t minus delta t and t plus delta t. So an uncertainty basically communicates a confidence interval. As I said, every measurement has an inherent uncertainty. There are 2 possibilities. That uncertainty is either instrumental or random. Now the question is, how do you tell the difference? If you look at these 2 examples here, the distance measured and the time measured, let's start with the distance. If you measured this distance over and over again, you'd probably get the same distance, 1.620 meters. So does that mean that there's no uncertainty in the distance? That's not true. It just means that the uncertainty in your distance measurement is smaller than the resolution of your instrument. So in this case, the resolution of your instrument is millimeters. It was measured with a meter stick, and so the resolution of your instrument is unable to distinguish uncertainties of 0.5 millimeter, because if it was more than 0.5 millimeter, you would have rounded up to 621, or if it was less than 0.5 millimeter, you rounded down to 619. So the uncertainty in the distance is instrumental, and it is 0.0005 meters, half of the smallest unit that my meter stick can measure. Okay. On the other hand, if you look at the time data, is this uncertainty instrumental or random? So the point I want to make here is that if you repeated the measurement 5 times and you got the same time every time, let's say 2.84 seconds, that means that your uncertainty would be instrumental, because you're repeating the measurement multiple times and you're getting the same answer. Okay? On the other hand, if you repeat the measurement 5 times and you get different values, the random variation in your ability to time the car is much greater than the instrumental uncertainty of the stopwatch. So in this case, your uncertainty is random. Okay? And so this is an either-or situation. You can't be random and instrumental. You can either be random or you can be instrumental, not both. So in this case, the time is random uncertainty, and the uncertainty in the time needs to come from estimating the spread in your data. And this is the tricky part, because we can get into very convoluted mathematics and calculated the standard deviation of the sample and so on and so forth. And in my opinion, this is too much work. So I think the simplest thing to do, all you want to do is quantify the spread in your data. And so the simplest thing to do is just to take largest minus smallest and divided by 2. In this case, that would be 3.15 minus 2.84 divided by 2, which is roughly equal to 0.15 seconds. So now I have two measured quantities. I have a distance and a time. I am going to use these two quantities to find the speed of the car. Very simple. Speed is distance divided by time. The next question that arises now is, I have two measured quantities that have associated uncertainties. And the question is, given that the time has an inherent uncertainty in it and the distance has inherent uncertainty in it, how uncertain is my calculated velocity? And this is where things can get very, very complicated. But what we are going to do is use something called the weakest link rule. And the weakest link rule says, pick the more uncertain of these two quantities, okay, whichever it is, and that uncertainty is the uncertainty in your velocity. So far we've talked about absolute uncertainties, and absolute uncertainties, as I said, define a confidence interval. I am confident that if you repeat my measurement, you'll measure a time between 3.004 minus 0.15 and 3.004 plus 0.15. Now, the question is that the absolute uncertainties do not tell you which is the more uncertain measurement. To figure out which is the more uncertain measurement, we need to switch to something else. We need to switch to a quantity called relative uncertainty. And relative uncertainty is basically a ratio of the absolute uncertainty to the size of the quantity that you've measured. And so this essentially gives you an estimate of the signal to noise ratio. And that gives you a sense of what is the more uncertain measurement. So the relative uncertainty in distance is equal to the ratio of the absolute uncertainty in the distance divided by the distance, which is equal to 0.0005 divided by 1.620, which is equal to 0.0003 or 0.03%. The important thing I want you to realize is that the relative uncertainty is a dimensionless quantity. It is a percentage or a fraction. It's basically telling you the ratio of noise to signal. I can do a similar calculation for the relative uncertainty in time. That's equal to the ratio of the absolute uncertainty in time divided by the time, which is equal to 0.15 divided by 3.004, which is equal to 0.05 or 5%. Now, the weakest link rule is a quick and dirty way to figure out how uncertain the velocity is. And the way it works is we simply take whatever is the worst uncertainty, clearly 5% is the worst uncertainty, and we say that if the relative uncertainty in the time is 5%, then the relative uncertainty in the velocity is 5%. So if the question comes up, what is the relative uncertainty in the velocity? It's 5%. You've already calculated it because it's the same as the relative uncertainty in time. So finally, if you want to find the absolute uncertainty in the velocity, I simply say that the absolute uncertainty in the velocity is equal to 0.05, 5% of the calculated velocity. That's equal to 0.05 times 0.54 meters per second, and that is equal to 0.03 meters per second. So finally, we can say that the measured velocity v is equal to 0.54 plus or minus 0.03 meters per second. And so finally, I want to discuss with you, why do we bother to do all this stuff with uncertainties? What we've done here is we performed an experiment to measure something, the speed of a toy car. And so what we want to do is convey to other people the confidence interval in our measurements. So if we put all the possible experiments on a number line, what I am saying is that I am confident that if you repeat my measurement, you will get a measurement somewhere between 0.51 meters per second and 0.57 meters per second. And why is this important? This is important because suppose another group performs the same experiment under the same conditions and gets a measurement of, say, v equals 0.56 meters per second. So now the question is, are these two measurements different or not? Okay, so naively you say, well, 0.54 and 0.56, well, it's not the same number. But the argument is, if team 2 measures the velocity to be 0.56 and it falls in the confidence interval between 0.51 and 0.57, then we say that our measurements agree to within experimental uncertainties. So this gives us a way to objectively compare whether we got consistent measurements or not. Okay? Let's suppose that, on the other hand, team 2 measures the velocity to be equal to 0.65 meters per second. Now 0.65 meters per second falls outside of the confidence interval of my measurements. And so the argument here would be that our measurements do not agree to the experimental uncertainty. So there's some inconsistency there that needs further investigation or explanation. And that is why we do uncertainties, because we want to be able to compare either one team's measurement to our measurement, or another possibility is maybe we made a prediction based on a hypothesis about something, and we want to compare whether our actual measured quantity is consistent with our predicted quantity. And again, in this case, the question is, does the predicted quantity fall inside the confidence interval of our measured quantity? If it doesn't fall outside the confidence interval. And if it falls inside, we say the measurements agree. If it falls outside, we say the measurements don't agree and there's something going on. Either you made a bad experiment, or there's really something inconsistent between the prediction and the actual measurement, and we actually need to go and investigate further what is going on.